Okay, in this video, we're going to be doing Calc BC Problem Set number 27. The problems in a playlist are in the description below. Let's take a look. Number 1, this is calculator, like the entire part 1. A particle moves in the xy plane along the path xy with derivative shown above. At t equals 1, the particle is at the point 5, negative 3. All right, so dx dt is e to the square root of t, and dy dt is sine of t squared. So we will not be integrating those by hand. A, write the equation line tangent to the particle's path at t equals 1. So to do this, we need to know the slope at t equals 1. So we're going to write down dy dx is equal to dy dt divided by dx dt. So I think it's important that you show that step, and then we have to evaluate this at 1. It's a calculator problem, so you could definitely use a calculator on this, but I decided to just do this one by hand because like the answer's sort of messy when you do it by hand, but I think it's good to see that that can happen. We know that the ordered pair is 5, negative 3. The biggest mistake I see with this, which is a little weird, people tend to use the t value as the x value accidentally, so make sure you're using x is 5, not x is 1, because x is not 1. All right, and then we're just going to write down our tangent line, and then we will move on to the next part. It is calculator though, so you could have used a calculator if you really wanted to. I'm going to leave my answer looking like this. Okay, next up. Find the particle's position at t equals 2. So what we want to do, it's a calculator problem, but we need to show some work. So what I'm going to do is I'm going to use the fundamental theorem to figure out the position of x at 2 and the position of y. So fundamental theorem, just your position at 2 is going to be where you are at 1 plus your displacement, which is the integral from 1 to 2 of x prime of t dt. And then for y, it's the same thing. Y of 2 is going to be where you are at 1 plus your displacement in the y direction, which is the integral from 1 to 2 of y prime of t dt. So now I'm going to use the calculator to find these values, then I'll come back and I will write my answer. Okay, so what I like to do on these is I like to store the function. So I always store the like dx dt, so the rate of change of x with respect to time, as dx of t. And then we're going to go colon equals, and it's going to be e, so I guess I'll use the key, e to the square root. I mean, I guess I can use the key for that. It's easier for me to type these things, but to show you where everything is, follow along on the emulator, and then press enter. Should say done. Let's store dy. So dy of t is going to be sine, which you can use the trig key for. I don't really want to. And then t squared. All right, so we're good with that. So we've written down our accumulation functions. What I'm going to do is I'm just going to have the calculator now kind of get the answer for us, right? So x of 1, we're told in the problem, is 5. And what we want to do is we want to add to that the integral. So I'm going to do shift and then plus. So it's the integral from 1 to 2. And then of, I'm going to press the var key, dx of t, and then t. And I will press, if I press just enter is going to give me a decimal no matter. Oh, no, it doesn't. Wow, it found an antiderivative? How did it do that? Let's go control enter. How did it integrate e to the square root of t? I'm going to go with 8.40753 or just 8.408. All right, I'm going to do the same idea for y. So y of 1 is negative 3. So this happens on the computer all the time because there's a difference between the negative sign and the minus sign. But I just hit minus on the keyboard and it's like, which did you mean? If you press that, that's the negative. So it's like the opposite of 3. And then I'm going to add to that our definite integral. I'll get the integral sign using the templates button this time. So templates, and then we go all the way to the end of this row. And we're going to go from 1 to 2. And it's dy of t dt. And control enter, because I don't want to deal with the fact that maybe it can integrate sine of t squared, which I'm confident it cannot do. So there we go. Those are our two values. I'm going to go back and do the handwritten part. See you there. Okay, and the final answer that we got is that our position at t equals 2 is 8.408 comma negative 2.505. All right, let's take a look at the next part. Find the maximum of the particle's y coordinate on the interval from 0 to 2. So it's a closed interval, absolute maximum. I'm thinking candidates test. I'm going to write down a function for y of t. So I'm going to say y of t is where we start plus our displacement, such as in this case is the integral from 1 to t of y prime of dummy variable. So I'm just using u and du. You wouldn't want to use x here, I don't think, because x is also like a part of the problem. This is definitely continuous. And therefore, we can say the absolute maximum will be at an endpoint or a critical point. And the reason for that is the candidates test. So I like to get that out of the way like right away. Then I can just do the problem. So we need to find the critical points. That's going to require the calculator. Let's see what that is. The calculator work here for part C. What I'm going to do first is I'm going to define y of t. So I'm just going to say y of t and then colon equals and just define it, right? I mean, we basically have it up here. I'm going to say, I'm going to paste that down and just change this to a t and then change these to dummy variables. So I'm going to use, I don't know, u, I guess. Okay, so now I have that set up. I also want to be able to find where y prime is equal to 0. So since y prime is sine of t squared, anything with trig, I think it's always better to just kind of do it on a graph page. So I'm going to say doc for, I'm going to insert a graph page. And I'm going to change the window. So menu for, it's a good idea to change a window before you graph a thing, because if the function is complicated, things will be like gross outside the exact window that you are specified. So I'm going to change that 0 to 2. Now I'm going to graph dy of, so I defined dy of t in part B, but I'm going to graph dy of x, because if I try to use t is not the variable when you're graphing in function mode, right? X is. So it'll just ask you if you want to create a slider, which is sort of like the error message telling you you're using the wrong variable. So press enter, graphs this. I'm going to press tab and graph 0. Then I'm going to do menu 8, 1, 4, and that's for intersection points. Click, click. 0, 0 is an intersection point. That's fine. I'm going to press escape, arrow over this. I mean, I'm going to hand write that number as well, but we're going to arrow over it. We're going to press control menu, which I can't show on the emulator for some reason, or it just doesn't show up when I press it. I'm going to store this as B, right? And press enter. Now it's bold, and if you arrow over, it'll say it's linked to B. This is going to be available in a calculator page. So we can see that we got, when y prime of t is equal to 0, we got t is approximately 1.77245. I like to use as many of those as I can. I'm going to store that on the calculator. You can see I did store that as B. Now what we need to do is we need to fill in our table that we're going to make. So it's t, it's the value of y, and we need to check 0, b, and 2. Let's go back to the calculator, get the calculator to spit out those values. So let's go back to our calculator page. And now I need to figure out the value of y at the endpoints and at b, and then we'll know the maximum value, right? So I'm just say y of 0 is negative 3.310. I'm going to do y of b is negative 2.415, and then y of 2 is negative 2.505. Okay, so now what we do is we're going to go back to the handwritten stuff, finish off this part. I'll see you there. And I'm just going to fill them in for us. So we got negative 3.310, negative 2.415, negative 2.505. And from this, we can see that the absolute maximum is negative 2.415 at approximately t is 1.772. I like to give both whenever possible because then I definitely have answered the question. All right, let's take a look at the next part. Find the particle's acceleration vector at t equals 1. So it's important that we write down the work, and then we're just going to use a calculator. So the acceleration vector at 1 is going to be x double prime of 1, comma y double prime of 1, or you might write, you know, like d squared x dt squared, comma dy d squared y over dy dt squared. I wouldn't write that, obviously, because I've screwed it up. And then do such that t equals 1. Whatever you want to do, I'm going to pop over to the calculator, get the values, and then I'll come back and write them. Okay, let's do the calculator part here for part D. We're trying to find the acceleration vector. We've already defined in part B dx of t and dy of t. So what I'm going to do is something that's, I don't know, kind of interesting. I'm going to have the calculator find the acceleration vector in like one shot. So what I'm going to do is shift minus for derivative, and I want the derivative with respect to t. And then what I'm going to put in here is a vector. So I'm going to say control, and then open parentheses. That's where we're going to put our vector. You can also get this, by the way, and maybe it's easier from the templates up, where is it? Row 2, column 3. There, because it's a 1 row, 2 column vector. There we go. So here I'm going to use the var key, dx of t. Press tab. Here I'm going to put dy of t. Now I'm going to use such that. It occurs to me that there's a faster way to do this by hand. Control equal, and then 1 to the left gets you such that. And then I'm going to say t equals 1, and press control enter, and I get 1.359, comma 1.081. Okay, so that's going to be our answer. Let me just really quickly show you a faster way to get to the derivative at a point, right? So it's menu, option 4 for calculus, option 2 for derivative at a point. I would say t is my variable, 1 is where I'm going to evaluate this thing. And then I would just put in my vector. So again, control, open parentheses, dx of t. I'm going to use a comma this time. And the calculator is just going to reformat it so that it works. And then dy of t, control enter. You can see we get the exact same answer. So either one of those approaches, using the calculus menu is definitely faster, I would say, on the handheld. If you're typing on a keyboard, either one is plenty fast. Okay, I'm going to go back and just pencil this in. See you there. Okay, and we saw on the calculator that our answers look like 1.359, comma 1.081. And let's take a look at one more part here. Find the particle's distance traveled on the interval from 1 to 2. So we know distance traveled is just the integral of speed. Speed for parametrics is the magnitude of the velocity vector. So we're doing integral from 1 to 2. It's going to be the square root of x prime squared plus y prime squared. Memorize that. Never get that wrong. You're just integrating speed, but like it feels a little bit different. Magnitude of velocity is what you're integrating. Just memorize it. Never get it wrong. Let's pop over to the calculator, see what we get. We have to do a definite integral. I'm going to show you 2 different ways that you can do this. One of them I think is the way that most people just do it, but it's going to be shift plus, I mean, we're directly typing in our arc length formula. So we're going to go from 1 to 2. We need to take a square root, so control and then x squared. We need dx of t, so I'm going to use the var key there of t, square that, plus dy of t, square that, and then tab all the way out. T is our variable. Press enter. We get 3.49291 or 3.493. Okay, that's how I think most people would do it. A slightly, potentially faster way, if you remember it and if you're, into doing this, would be same thing here. And then what I'm going to do is I'm actually just going to ask the calculator to find the norm of the velocity vector. So that's going to be menu 7 for matrix and vector, option 7 for norms, and then in there you want option 1 for norm. So that's a little weird, but I want the norm of the velocity vector. So that's going to be control and then open parentheses, dx of t, comma dy of t. I mean, basically at this point I'm just showing you will get the same answer, t. So I like this because, I don't know, you're frequently asked for like acceleration vector, velocity vector, arc length. All of those can be based on the velocity vector, and then you can just kind of like jump off of that to get this arc length. So same answer either way. All right, I'm going to go back, I guess, write in the numerical value. I will see you there. All right, and our calculator told us it's approximately 3.493. And we got one more question to do here. This is a non-calculator question. We're given x prime and we're given y prime, shown above. We want to find the second derivative. All right, so we know that to find dy dx, we're going to do dy dt divided by dx dt. So let's start off with that, write it down. So that's going to give us, we're just subbing in here, 2t plus 5 cubed over 3t plus 1 squared. Now we need to find the second derivative. This is an important, like, easy to calculate thing, but easy to screw up because, like, if you underthink this, you will get it wrong. If you overthink it, you'll get it wrong. You have to be right in the right thinking domain. All right, so we're going to do the derivative with respect to t of dy dx, which is dy dx is that thing above. That's going to require the quotient rule just to find the derivative of that. Then we're going to divide that by dx dt. And dx dt is already given. We already know that. All right, so the derivative with respect to t of dy dx, bottom. Derivative of the top is going to be 3 times 2, so 6, quantity 2t plus 5 squared, plus, minus, because it's quotient rule, sorry. Bottom derivative of the top minus top. Derivative of the bottom. You shouldn't really talk while you do the quotient rule. You end up screwing it up, but there we go. All over the bottom squared, which takes us up to the 4th power because it's already squared. And then all over the original dx dt. And then there's like some algebra we can do, right? So for example, we can take out a 6, we can take out a 3t plus 1, and we can take out a 2t plus 5 squared. When we do that, all that we're left with when you simplify it is t minus 4 in that numerator. The denominator is going to be our thing to the 4th, and then the thing to the 2nd is the same, so we end up with the thing to the 6th. We have this. And finally, there's a 3t plus 1 in the numerator and a 3t plus 1 to the 6th, so we can cancel those. Our final answer is going to look like 6, quantity 2t plus 5 squared, quantity t minus 4, all over 3t plus 1 to the 5th. I think this is more annoying than anything you would find on like the actual AP exam, but it's definitely a fair question for class because it practices a lot of Calc AB stuff, a lot of Calc BC stuff. Anyway, that's the entire problem set. I hope this was helpful, and good luck.